Hi there, I'm Nelson Rogers, and today I'll be presenting about grand strategy in the well-known board game Settlers of Catan. This is going to be an inductive process in which we try to come about the best strategies for achieving victory in this game. The full explanation can be found in my paper, Grand Strategy in the Settlers of Catan, an inductive process. We're going to begin by looking at what our assumptions are for the game. Because as we know, we have to define kind of the world that we're working in, the rules that we must play by, per se. Now, the goal of the game is to get victory points. You amass victory points by trading in resources, and so the goal is to accumulate 10 victory points. We're going to abbreviate victory points to VP. This will help us when we get to the kind of mathematical part and we start defining variables and stuff like that. So goal is 10 victory points. Now, what isn't it's interesting to note is that you begin the game with 2 victory points because of the initially placed settlements that you have. So what we're actually trying to achieve is earning an additional 8 victory points. Now, it's also important to note that there are many variations to the game of Catan. There are many expansion packs, there are variations depending on how many players, and the strategy is greatly affected by these things. So for the game that we're going to be playing today, we will primarily be focusing on a regular game, no expansion packs, with 4 players playing by all the normal rules, so no house rules in this one. Now, before we jump into the body of it, I just want to explain kind of what the genesis of this was. I myself really do enjoy playing the game, but I kind of always had this mathematical inclination to pursue kind of what is objectively rational. And so equipped with the tools of game theory, statistics, calculus, mathematics, we really actually have the ability to quantify, if you will, or express in a quantitative way what is correct, if you will, correct for the rational agent to do. And I really do have a passion for this area of academia, and this was just kind of a natural extension of that passion, if you will. So, without further ado, what we first need to examine is how do we earn victory points? How do we earn the additional 8 to get to the total of 10? Well, there are 5 ways we do this. The first way is with settlements. Settlements are worth 1 victory point, and they require 1 lumber, 1 sheep, 1 wheat, and 1 brick. Just as a kind of a shorthand, we'll be using the cursive L, or L in the mathematical equations to express lumber. We'll be using W to express wheat. We will be using B to express brick, and we'll be using S to express sheep. The final resource is ore, O-R-E. However, it can be kind of challenging when we're using the variable O. So for ore, we're actually going to use R. So R is going to be for our ore. And it's worth noting that a settlement is 1 victory point. Now we can also build cities. Cities take 2 wheat and 3 ore. Here's the 2 wheat, here's the 3 ore we were talking about, that variable R for ore. Now, when a player upgrades their settlement into a city, that city is now worth 2 victory points. But because you already have 1 victory point from the settlement, the city, these resources are actually worth only 1 victory point. The third way we can earn victory points in this game, or should I say the next 3 ways, are via development cards. The first of these 3 ways is instantaneous victory point cards. We'll be abbreviating instantaneous victory point card to IVP so that when we get to mathematics, it works a little bit easier. Now, each of these instantaneous victory point cards is worth 1 victory point. However, we have to factor in the probability of drawing an instantaneous victory point card from a deck of 25 development cards. Of the 25 development cards, 5 of them are immediate victory points. Now, we can then do an expected value problem to arrive at the value of drawing 1 card. And we know that 1 development card is equal to 1 sheep, 1 wheat, and 1 ore. We will now carry out a simple expected value problem analysis in which we determine the probability of drawing an IVP from the 25 card deck. Take this probability of 0.2 and multiply it times the value of the IVP, which is 1 victory point, to arrive at an expected value of 0.2 victory points from drawing 1 development card based on the fact that an IVP yields 1 victory point. The next way we go about earning victory points is through the largest army card. Now, a player receives the largest army card when they have 3 knights. Knights are individual development cards that are the knight card, which means a player must draw 3 knight cards from the development card deck. And each of these knight cards are simply a development card with the same cost. 1 sheep, 1 wheat, and 1 ore. As such, we can carry out a binomial probability to determine what the expected value is for the largest army. So as we can see here, the expected value of the largest army card, given that a player draws 3 knights consecutively, is 0.352. Now, what exactly does this expected value equal? Great question. This expected value of 0.352 victory points equals 3 wheat plus 3 ore plus 3 sheep. So those 9 resources together have an expected value when given to development cards with the expectation of drawing knights of yielding a 0.352 victory points value. The fifth and final way that a player can go about earning development cards in a game that we've outlined is by earning the longest road card. This is given to the player that has the longest consecutive road beyond 5 roads. Now, the longest road card, exactly like the largest army card, is worth 2 victory points. We can then equate these victory points given the resources that we would expect a player to use to get these victory points. And given experience, given empirical data that we have, it's reasonable for us to expect that a player who is in pursuit of the longest road card will build an additional 11 roads in addition to the 2 that they get at the beginning of the game. "11 brick plus 11 lumber equals 2 victory points in the case that we've outlined. Now, we've outlined several ways which we can go about earning victory points. We've actually outlined 5. And from these methods, we can actually build a matrix to solve for the values of each of the resources with respect to one another. This first matrix we've constructed, we're going to call it matrix A. And this matrix outlines all the resources that we need for a respective item. So, for example, if we take a look at line 2 of our matrix, row 2, this is going to be our column for wheat. This is going to be our column for ore. And we see that the 2 wheat and the 3 ore make a city. This will all make a little more sense when we construct our other matrices. This is now our variable matrix. So we can see that we have the lumber and brick, and I'll explain why that is in a minute, wheat, sheep, and ore. Now, if we actually refer back to our first matrix, you might notice something interesting about it. In this bottom left corner here, we have number 22, but this doesn't actually appear anywhere in our analysis that we previously performed. Now, what's interesting about this is that with the 22 resources, we can see that lumber and brick are functionally one and the same. We look at the road, the longest road card, and the settlement, which are the only two things that require lumber and brick, and they actually require the same amount, which means that in this variation of the game we're playing, they are essentially the same resource. Now, the reason why they can't have their own column is because then we cannot find an inverse matrix and complete our matrix operations to determine the value of each individual variable as we outlined here. We're now going to enter our last matrix, which is going to be the values that we found earlier. Now we can see here that just with a few basic matrix operations, we can actually find what these variables equal, which is very, very interesting because then we're actually ascribing a quantitative value to each resource relative to one another, which really helps us in determining strategies later throughout the game. I'm going to demonstrate the matrix operations with these letters down here so that we don't have to rewrite this over and over again. Now, through simple inversion of the first matrix here, multiplying that now by our C matrix, which is going to be the values we determined earlier through our analysis, we actually have found the values for the variables in the B matrix. We can see here there's the inverse of A multiplied by our expected values to find the values of the variables. Because like matrix is essentially just a system of equations, and these are our variables. So as we can see here, these are actually the values of the resources in the game Catan. Now, some interesting observations about this matrix. First, lumber and brick are small positive values. This indicates that by themselves, there is in fact value to holding them. We then look at wheat, which seems disproportionately valuable relative to the rest of the resources that we've outlined based on their value. However, wheat is used to make cities, it is used to make development cards, settlements, lots of uses for wheat. And so it's kind of intuitive, in fact, that we would have such a high value. Now we compare this to sheep and ore, and they're actually rather large negative values. So why do we think this would be? Given that, the possibilities that are associated with them and what they can produce. Why do we think this could be? Well, the answer lies in how these two bottom resources are combined with the others, namely wheat. So we see that when a sheep is combined with a wheat, when a ore is combined with a wheat, that when sheep and ore are combined with wheat, we actually have larger gains based on the fact that wheat has such a high value. Because really, we would never see wheat in its very pure state being 1.42 victory points all into itself, given the fact that we've multiplied it by 100 for easiness of arithmetic. And so what we really have to analyze is the combinations of these resources. And that is really where we kind of get into the fun math, if you will. Now that we've defined our variables, it's time to turn our attention to the board itself. Here I have a randomly generated Catan board. We can see the hexagonal structure of every individual tile, each with a number on it. And so how the game flows is the player will roll the die on his or her turn, and the number that is created by the die is the hexes that yield resources. So, for example, we see down here, if a player rolls an 8, then this resource, which, although it's fuzzy, appears to be a lumber hex, will yield lumber to whichever players have settlements surrounding that hex. What we must do next is look at the probability of each individual hex. Because, for example, a hex that is surrounded by 2s and 12s is practically worthless, given the fact that those numbers are rolled so seldom. Now, if we compare that to a hex that is surrounded by 6s and 8s, that's much more favorable to the player whose settlement or city is on that hex, or on that intersection point, if you will. It's important to note at this point that the 7 is reserved for the robber, which is something we won't really be getting into in this exercise. But it's important to know that 2 through 6 and 8 through 12 are the numbers that will yield us our resources. We're now going to construct a distribution, a probability distribution for the dice to determine what the most probable rolls are. We're going to visualize that. So here we have a probability distribution for the dice. We obviously see that a 7 is the most probable roll. A 12 and 2 are equally improbable, since there's only one combination for each of those that will respectively produce that number. Now, what is the one thing that will make an equation scary? That's right, sigma notation. So let's dive right into it. We can determine the value of what that settlement produces based on the expected value of every single tile. So we can derive a very simple equation, actually, that shows us that the value of what a hex produces is the summation of the expected values. Now, perhaps this equation looks a bit scary from a distance, but when we examine it, it's actually fairly simple. All it's saying is that for a given number of hexes, h, which a settlement is adjacent to, we sum the values of that resource times that probability. And this will give us the value of a settlement's production, a value of each settlement, if you will. We can run simulations using this equation and randomly generated boards. One, for example. In this example, we're examining a settlement that is adjacent to 2 sheep and 1 lumber. The numbers on those 2 sheep and 1 lumber are 9, 6, and 11 respectively. We can fill in the values then to illustrate what the value of the settlement's production is. So as we can see, sheep are both worth negative 60.91 victory points when we multiply victory points by 100. The lumber is 4.55. The probability of each of these numbers, 9 is 0.1111, 6 is 0.1389, and 11 is 0.0556. So there is this probability of receiving this many resources on any given roll. So we simply find the expected value by multiplying across, and then we add the sums of those expected values. This example. As we can see, the production of this particular settlement is actually negative. Now, is that a bad thing? Maybe, maybe not. If a player's other settlement is also negative, then perhaps it is a bad thing because we won't actually be able to produce very much without wheat. Wheat is namely the one thing that will offset, a poor resource, a poor settlement. Here are 4 additional simulations. For the purpose of the data, I've conducted many simulations to arrive at the conclusion that there is in fact validity to this equation. We see that those settlements that have wheat are typically much more valuable than those that are entirely composed of lumber, entirely composed of sheep, things like that. Now, we also can construct... Now, it's also worth noting a few other kind of examples and observations about this method. One is that if a player is going for the longest road strategy and places their settlement on some combination of brick and lumber, brick, lumber, lumber, brick, lumber, brick, things of that nature, then they're guaranteed to have a positive value for their settlement because we know that with the resources they have, they can in fact produce victory points, that longest road card. Now, what's also notable is that if a player is going for the city strategy, for example, where they'll build a lot of cities, they're going to want to be around a lot of wheat, a lot of ore. But what's noteworthy about that is that the value of the wheat will quite frankly offset the cost of the ore. And so wheat is sort of the great equalizer in all this. Even though that sheep and ore are both negatively priced, we actually see that wheat is so valuable because it can be used in settlements and in cities and development cards, the latter two of which also require sheep and ore, the negative things. Now, I'd like to leave you with one final thought, an axiom of this equation, if you will, or perhaps it's the other way around. Is this equation right here, the total value of production equation. Now, why is it different, or how is it different from this one? Well, in this total value equation, we're not looking at one specific settlement. We're looking at an entire player's arsenal, if you will. The combination, the expected values of all of their resources that they're adjacent to and can receive. So here, at the beginning of the game, this value could theoretically range from 2 to 6 hexes that produce. If a player, the extreme situations would be 2, where a player places their resources just on the outskirts of the board where they're only touching one hex. The other extreme, which is much more common and quite frankly the norm, is where a player has 6 hexes that they are adjacent to receiving resources from, because each of their settlements is on the board in a place where all the hexes around it produce resources. This equation is really helpful because it determines the total value of what a player's production is. So while we look at this equation, it might produce a negative value, and we are okay with that because we need some resources to pair with others to create larger values. This one, we really do in fact want to maximize because this is what's going to be really telling of our ability to produce resources and a strategy that will win the game. Now, there are several other parts that can be found in the paper. Several theorems that I've created can be found, some axioms to pair with those, as well as 3 analyses of specific strategy, or the largest army strategy, the longest road strategy, and the city strategy. 3 fairly common strategies. Once again, thank you for joining me today as we explore the rational side of Catan and try to make reason of all that is irrational around us. Thank you.